In this example, we'll look at simulation and optimization in Solid Edge and the benefits it brings to design engineers. Solid Edge simulation offers several different types of simulation analysis. The first that we're exploring today is beam analysis. Here, we have an engine hoist that needs to be tested to ensure that it is strong enough to hold the target weight. Using beam analysis is an efficient way for designers to quickly validate the strength of their parts, as it focuses solely on frame elements, eliminating the time and resource required to analyze complex shapes and features. When creating analyses in Solid Edge, there is a consistent and intuitive workflow followed. From defining the geometry that makes up the study, setting the appropriate loads that the part or assembly will be seeing, to setting constraints to simulate proper reactions from the elements making up the study, Solid Edge simulation allows you to create real-life scenarios on your 3D parts. For our engine hoist, we need to make sure that it can hold the 20,000 Newton force that it's rated for. Once the study is set up, running a beam analysis is very fast and efficient, as Solid Edge simulation doesn't need to worry about the exact frame geometry to solve for the reaction forces on its members. A huge benefit, especially when working with very large framework assemblies. Once solved, Solid Edge provides us with an easy-to-understand readout of the results, showing that the hoist stresses are well below the yield stress. No failures taking place here. However, if you're thinking to yourself, "I've never had a design fail due to stress," how about this? A lesser known, but just as important use for Solid Edge simulation is to check to see if assemblies are overbuilt and spending more money than necessary on stock materials. For example, it's apparent that these two support frame members on the back of the assembly are overkill for the amount of stress exerted on them. Of course, making changes in Solid Edge is simple. A quick and easy edit of both of the frames to something a bit smaller, and Solid Edge is already saving us money on the less expensive stock. Once the frames have been changed out, we'll simply rerun the simulation study that's already been created. Viewing the results from the change, we can see that these tubes are much more appropriate than the previous, and we're still well under our yield stress. In addition to frame analysis, Solid Edge simulation offers several other study types. Next, let's look at how Solid Edge can use both surface bodies and solids to optimize both speed and accuracy on a more complex assembly. The leveler is made up of a threaded bolt running through an adjustment bracket used to control the balance of the engine being held. We have a requirement that the bolt can't bend more than 1 millimeter or the adjustment bracket won't work properly. To optimize the simulation analysis on the leveler, we can easily represent our sheet metal end caps as surfaces, a much more lightweight representation for the study. Mixing surfaces and general bodies is a great way to simulate sheet metal bodies along with formed parts. Now that the end caps are defined, it's time to set up the study. Setting up studies on assemblies is very similar to how we did in the beam analysis. We have to define our geometry, loads, and constraints, exactly like in the beam analysis. But this time around, unlike the beam analysis, we need to define how the parts connect together. With the beam analysis, connections are made based on how the frame cross-sections were created. But now, we're working with more than just frames, so we need to define them using any of Solid Edge's great tools. Available connection options consist of bolted, edge, and manual definition. However, one of the best time-saving options in Solid Edge simulation is the auto connection command, quickly creating all the connections automatically. Now that everything is set up, it's time to mesh and solve the study. Of course, Solid Edge gives users complete control over mesh settings for both solid and surface meshes. However, for this study, we'll just keep the default values as they've been optimized to provide accuracy and speed. Our primary interest in this study is displacement, not stress distribution. An easy change using the drop-down of the results we wish to view. An animation shows exactly how this part will deform as it is loaded. Using the bolt as a reference, it's easy to see that there is too much flex in the leveler. Of course, with Solid Edge's synchronous technology, we could easily resize the beam manually to find the best solution, adjusting the overall length and thickness to make the beam stronger. However, rather than manually making changes and rerunning the study each time to check if they'll work, Solid Edge Simulation offers a game-changing tool that takes all of the hard work out of optimizing your designs for simulation. I introduce to you Simulation Optimization. Simulation Optimization is a wizard-based tool that allows users to define objectives of simulation studies and customize how their parts can change in order to converge on the most optimized version. Here, we can set our objective of maximum displacement of 1 millimeter. The next steps include defining limits of the parts, such as stresses that they cannot exceed, and finally, defining which variables that we wish to solve on. This can be a single variable or multiple variables, as here we'll adjust on the length and the thickness of the bracketry to optimize its size. The remainder of the options simply define what is considered solved on the study. Once again, settings optimized by Solid Edge so we can simply keep the defaults. Once we begin the optimization, we see that as it iterates, it's simply taking the values of each subsequent study to make closer approximations to what the most optimized condition will be. Just imagine how long this would take to run each of these studies independently. Of course, running through iterations takes time, but since it's all automated, this time could easily be spent on other tasks, or maybe even just going and getting a cup of coffee, because in the end, Solid Edge is going to provide you with a comprehensive summary of all of the studies and their associated values. The optimization summary is produced in Microsoft Excel, allowing us to easily customize the output if we so desire. We see the study optimized the leveler and provided us with values for the size of the beam, all in a fraction of the time. Once optimized, any results, including animations, can be output or saved off for design reviews, marketing materials, or any other use needed in your design workflows. Of course, generating a report in Solid Edge Simulation is a breeze. Automating the creation of screen captures of study results and all of the pertinent information to provide that information to you in whatever format you choose. As you can see, Solid Edge Simulation is perfect for design engineers, from making sure your designs are appropriate for their purpose, providing a simple and intuitive method for setting up studies, to a full optimization capability that can solve multiple variables with minimal designer input. Solid Edge Simulation truly provides a valuable solution to design engineers. Oh, and rest easy knowing that all of this is done leveraging FEMAP and Nastran, industry-leading simulation technology. Solid Edge, design better.